Hey there folks, Zack here. In this video, I'm going to give you a quick preview of what you can expect to see in week 12, and I'm going to do so through the following example. Here, I've given you two objects, and in each case, we're going to try to think about the total mass of the object given its mass density function. On the left, we're dealing with a two-dimensional object D. Maybe this is like a thin, flat steel plate living in the xy plane. We're told that at the point xy, this object's mass density is given by x times y kilograms per meters squared. Well, if we know the density function, we can integrate that function to get the total mass. The total mass of our plate is the double integral throughout d of sigma xy dA. And this is something that we can actually compute. I'll leave it as an exercise for you to set up and evaluate this double integral. But what you should find is that the total mass is 30 kilograms. Okay, what about this object E on the right? This is a three-dimensional solid whose mass density at the point x, y, z is given by x times y times z kilograms per meters cubed. Again, we're looking for the total mass. Well, based on what we know in the two-dimensional setting, maybe we could integrate this density function to find the total mass. The trouble is, we don't currently know how to integrate a function of three variables, and we don't know how to integrate throughout a three-dimensional domain. These are notions that will be introduced in week 12 when we talk about triple integrals. As you'll soon see, our methods for defining and evaluating triple integrals are very similar to our methods from double integrals. And it turns out that the connection between mass density and total mass holds in this setting as well. So the total mass of our solid is going to be the triple integral throughout E of our density function sigma xyz. Now, after we've formally introduced triple integrals and you try some examples for yourself, I'd like you to come back to this problem. See if you can use triple integrals to show that the total mass of this solid is 45 kilograms. During our unit on double integrals, we saw that choosing the right coordinate system can make a huge difference in our integration. Well, the same is true for triple integrals. Later in week 12, we'll see that our change of variables formula that we know and love from the two-variable setting extends very nicely to a formula in the three-variable setting. This will allow us to change our coordinate systems to make setting up and evaluating triple integrals much easier. As a special case of this formula, we learned how to evaluate double integrals in polar coordinates. Well, in the three-variable setting, we have a couple different analogs of polar coordinates, namely cylindrical or spherical coordinates. Perhaps not surprisingly, we'll be able to use our three-variable change of variables formula to integrate in these coordinate systems as well. As you'll soon see, this can be particularly helpful when integrating throughout a 3D domain whose boundaries are given by cylinders, cones, or spheres.